Today, we'll design a system for realistic human face generation. The idea is to take random noise as input and transform it into photorealistic images of faces. This task isn't just a technical challenge, it also has important applications in entertainment, virtual reality, gaming, content creation, and even anonymization for privacy. We'll begin by clarifying the requirements. What's the primary application? Should we support diverse faces across ages, genders, and ethnicities? What resolution do we need? And what latency is acceptable for generating images in real time? From there, we'll frame the problem as a generative modeling task, comparing different approaches, VAEs, GANs, autoregressive models, and diffusion models. Each has strengths and weaknesses, but for this problem, we'll select GANs as the best trade-off between speed, realism, and controllability. We'll then move into data preparation, collecting diverse, high-quality face datasets, cleaning them, augmenting for variability, normalizing, and ensuring fairness in representation. Next, we'll dive into model development, where we'll explore the generator and discriminator architecture, the adversarial training process, and how to address challenges like vanishing gradients, mode collapse, and training instability. Finally, we'll discuss sampling strategies, evaluation metrics like FID and inception score, and system design, including how to set up training, evaluation, and deployment services for a continuously improving face generator. By the end of this session, you'll see how to build a pipeline that produces diverse, high-quality, and realistic human faces with state-of-the-art generative models. The problem is to design a system to generate human face images. Here are some good requirements to ask. What's the primary application of this system? Is the focus only on faces? Should we generate a diverse range of ages, genders, and ethnicities? What's the desired image resolution? What's the latency requirement? We're framing our problem as human face generation. Given a user request, the system should produce a realistic, diverse, and controllable image of a human face. The input to our generative model is a random noise vector z tilde operator n, 0, 1, z /sim /mathcal n 0, 1. This noise vector is crucial because it ensures variation. Even small changes in ZZ can produce drastically different outputs. Our output is a photorealistic face image that meets quality benchmarks for resolution, realism, and diversity. Before selecting our model architecture, we systematically evaluated 4 major families of generative models. 1. Variational autoencoders, VAEs. Mechanism. Encoder maps an image into a latent vector ZZ, capturing compressed semantic information. Decoder maps ZZ back into pixel space to reconstruct an image. Strengths. Simpler to implement, stable training dynamics. Efficient inference, fast image generation. Latent space supports interpolation and some editing tasks. Weaknesses. Faces often lack photorealistic detail. Generated outputs may appear blurry due to probabilistic reconstruction loss, MSE, or KL regularized ELBO. Limited control over fine-grained features like lighting or facial expressions. 2. Generative adversarial networks, GANs. Mechanism. Generator GG transforms noise ZZ into an image. Discriminator DD classifies images as real or fake. Adversarial training minimizes min-max DV, G, D, /min _ G /max _ DV, G, D, to push GG toward realism. Strengths. State-of-the-art for high-resolution, high-fidelity face synthesis, e.g., style GAN3. Fast inference after training, a single forward pass from ZZ to image. Can incorporate attribute control via conditional GANs, CGAN, or latent space manipulation. Weaknesses. Training can be unstable, mode collapse, non-convergence. Sensitive to hyperparameters and architecture tuning. 3. Autoregressive models. Mechanism. Model images as a sequence of discrete tokens, pixels, or patches. Each token is predicted conditioned on previously generated tokens. Often implemented with transformers for long-range dependencies. Strengths. Excellent detail and realism, fine control over structure. Stable training via maximum likelihood. Weaknesses. Very slow generation, each token or patch is generated sequentially. Memory intensive for high-resolution images. 4. Diffusion models. Mechanism. Forward process gradually adds Gaussian noise to an image until it's pure noise. Reverse process, trained neural network learns to denoise step by step to recover the image. Strengths. Exceptional image quality, fine detail. Robust to noisy or partial inputs. Stable training, no adversarial instability. Weaknesses. Slow inference, requires dozens to hundreds of denoising steps. Heavy compute cost for high resolution. Our decision, GANs. Chosen for balance of speed, quality, and control. With modern architectures like Style GAN, we can achieve 1024 by 1024 photorealistic outputs in milliseconds per image at inference. The latent space supports feature editing, age, hairstyle, lighting, making it useful for applications requiring customization. Training instability can be managed with techniques like spectral normalization, Wasserstein loss with gradient penalty, and progressive growing. In summary, while VAEs, autoregressive, and diffusion models have their own merits, GANs provide the optimal trade-off for interactive, high-quality human face generation in a production system. In the context of training a face generation model, the quality of the dataset directly impacts the realism, diversity, and fairness of the generated outputs. The data preparation stage is therefore critical to ensure that the model learns from clean, representative, and well-structured data. Remove low-quality images. Begin by filtering out images that are blurry, heavily pixelated, have extreme lighting conditions, or contain obstructions that hide facial features. Low-quality inputs can cause the model to learn noise patterns, which can manifest as artifacts in generated faces. This step can be automated using sharpness detection algorithms or face detection confidence scores, but manual inspection is often necessary for edge cases. Augment images. Data augmentation increases the effective size of the dataset and helps the model generalize better. Common techniques include horizontal flipping, slight rotations, random cropping, and color jittering. In the face domain, augmentation should preserve the natural structure of the face. Overly aggressive transformations, e.g., large rotations or extreme warps, can confuse the model. For diversity in training, simulate real-world variability such as different lighting conditions, small facial occlusions, or slight changes in expression. Normalize images. Standardize image size, e.g., 256 by 256 pixels, so that all samples have a consistent resolution, which simplifies batching and training. Normalize pixel values, e.g., scale to 0, 1, or standardize to 0 mean unit variance, to stabilize training and improve convergence. This step also includes aligning faces, using facial landmarks to ensure that eyes, nose, and mouth are consistently positioned across the dataset, reducing positional variance. Enhance diversity. A high-quality face generation model must learn a wide variety of facial attributes, age groups, genders, ethnicities, hairstyles, and expressions. Actively ensure that the dataset covers underrepresented groups to avoid biased outputs. If the initial dataset is skewed, complement it with additional images from other sources to balance the representation. This diversity not only improves fairness but also increases the creativity and variability of generated outputs. Key takeaway. The data preparation stage is not just about cleaning and resizing images, it's about shaping the entire learning experience for the model. A carefully prepared dataset leads to faster training, higher image fidelity, and more inclusive, realistic results. Our model architecture follows the standard generative adversarial network structure, which includes two key components, the generator and the discriminator. These two networks work in an adversarial setup. The generator's job is to produce realistic human faces, while the discriminator's job is to tell apart real faces from generated ones. 1. Generator. The input to the generator is a random noise vector, typically sampled from a Gaussian distribution. The generator is made up of upsampling blocks, which progressively transform this low-dimensional noise into a high-resolution image. Transposed convolutions, upsampling convolutions, are used to increase spatial resolution. Unlike normal convolution, they expand the feature maps by inserting zeros between pixels before applying filters, allowing us to grow the image size step by step until we reach the target resolution, e.g., 256 by 256. A normalization layer follows most convolution operations to stabilize training and maintain consistent feature scaling. This can be batch normalization, instance normalization, etc., depending on the training stability and dataset characteristics. We also use nonlinear activations, e.g., ReLU or leaky ReLU, after each block to allow the network to learn complex transformations that map noise into coherent face structures. 2. Discriminator. The discriminator's input is an image, either a real human face from the training set or one generated by the generator. It uses downsampling blocks that gradually reduce spatial resolution while extracting more abstract and discriminative features at each step. These extracted features are then passed through a classification head, often a fully connected layer with a sigmoid activation, to output a probability indicating whether the input image is real. During training, the discriminator provides feedback to the generator, effectively teaching it how to create more realistic faces over time. Interaction between the two. The generator improves by trying to fool the discriminator, while the discriminator improves by better spotting fakes. Over multiple iterations, this adversarial process pushes the generator to produce highly realistic and diverse human faces. In the training phase, the generator and discriminator are locked in an adversarial game. The generator starts with random noise and tries to produce realistic faces, while the discriminator learns to distinguish between real and generated images. Over many iterations, the generator uses the discriminator's feedback to improve, and the discriminator adapts to spot the generator's latest tricks. This process continues until the generator's faces are convincing enough that the discriminator can no longer reliably tell them apart from real ones. The core learning objective is the GAN minimax loss. Generator: minimize the loss, make fakes indistinguishable from real. Discriminator: maximize the loss, detect fakes as accurately as possible. This tug-of-war drives both networks to improve together. Key training challenges and solutions. Vanishing gradients. When the discriminator becomes too good, it gives the generator almost no useful feedback, gradients near zero. Solutions: balance learning rates, add label smoothing, use feature matching, or switch to Wasserstein GAN with gradient penalty for more stable gradients. Mode collapse. The generator finds a few safe outputs that reliably fool the discriminator and keeps repeating them, reducing diversity. Solutions: introduce mini-batch discrimination, so the discriminator looks at image batches, use unrolled GANs, apply noise injection, or regularize with diversity-promoting loss terms. Failure to converge. GAN training oscillates without settling, often because improvements in the generator degrade discriminator performance too quickly. Solutions: train the discriminator for multiple steps per generator step, apply spectral normalization to stabilize discriminator weights, or use progressive growing, start with low-resolution images and increase resolution gradually. Training instability. Small hyperparameter changes can cause large swings in performance. Solutions: carefully tune batch size, optimizer parameters, atom with beta 1 is almost equal to 0.5 often works well, and ensure dataset normalization is consistent. By tackling these issues systematically, the training process can produce a generator capable of creating highly realistic, diverse human faces with stable performance over time. In the sampling stage, we generate new face images by navigating the model's latent space, which is a high-dimensional space where each point corresponds to a possible input noise vector for the generator. Latent space can be thought of as the imagination space of the model. Each vector sampled from this space is transformed by the generator into a unique face image. The simplest approach is random sampling from a standard Gaussian distribution. Here, we pick latent vectors uniformly from the whole space, producing a wide variety of faces with diverse features. However, sometimes random sampling can generate less realistic or extreme images that lie in the less probable regions of the latent space. To address this, we use truncated sampling, which restricts sampling to a smaller, high-probability region within the latent space. This truncation improves the overall quality and realism of generated faces by avoiding unlikely vectors that produce artifacts or unnatural images. By adjusting the truncation threshold, we balance diversity, variety in generated faces, and quality, realism and fidelity. A lower truncation value leads to safer, more polished images but less variety, while a higher value produces more novel but occasionally flawed faces. This sampling strategy is key to controlling the output characteristics of the face generator, enabling applications that require both realism and diversity. Evaluating the quality of generated human faces is crucial to ensure the model produces realistic and diverse images. We use both offline and online metrics to get a comprehensive understanding of performance. Offline metrics focus on quantitative assessment using established statistical measures. The Inception score, IS, uses a pre-trained image classifier like Inception v3. It evaluates how confidently the classifier assigns a label to a generated image and how diverse those labels are across many images. A higher IS indicates images that look like distinct, recognizable faces. The Freshet Inception distance as FID compares the distribution of generated images to that of real images by measuring the distance between their feature representations in the pre-trained network. Lower FID scores mean the generated images are closer to real ones in terms of quality and diversity. Human evaluation remains essential, where experts or users visually assess the realism, diversity, and appeal of generated faces, catching nuances that automated metrics might miss. Online metrics involve real-world interaction data. User feedback helps understand how end users perceive the generated images, providing insights on acceptability, trust, and usefulness. Latency measures how quickly images are generated and delivered, affecting user experience especially in interactive applications. Together, these metrics guide model improvements by balancing visual fidelity, diversity, and responsiveness. Designing a robust human face generation system involves multiple interconnected components to ensure continuous improvement, reliability, and quality output. Face generator. This is the core component that takes random noise vectors as input and generates realistic human face images. It leverages the trained GAN model to create diverse and high-fidelity faces in real time. Training service. To keep the face generator up to date and improve its capabilities, the training service continually retrains the GAN model. This retraining uses newly collected, user-approved images as well as additional training data. This continuous learning helps the system adapt to new styles, fix shortcomings, and enhance image realism. Evaluation service. After retraining, the evaluation service rigorously assesses the new GAN model against offline metrics, human evaluations, and production benchmarks. Only if the new model demonstrates clear improvements in quality and performance will it be approved to replace the existing model. This ensures stable, high-quality outputs without regression. Deployment service. Once approved, the deployment service seamlessly rolls out the updated model to production. It handles version control, model loading, and ensures minimal downtime so users always have access to the latest and best model. Together, these components form a closed feedback loop that maintains model quality, incorporates user feedback, and delivers consistent, realistic human face generation.